Hi, everyone. My name is Purvi Goyal. I work as a principal product manager at AWS. I've been focusing on Windows containers and compute platforms at the moment, and I've been here for a little over 5 years now.
Hello, everyone. My name is Mars Morales. I work as a principal solution architect at AWS, and I specialize on Microsoft workloads on AWS platform.
Hi, everyone. We are here for the third and final episode of the Virtual Workshop on Windows platform and experiences on AWS. In the last two episodes, you learned about how to streamline management of Windows workloads and how to build golden images and deploy resources for third-party applications on AWS. In the current episode, we will talk to you about how you can effectively run your Windows server on Amazon EC2 and container platforms. We'll be giving you a walkthrough of some of the key capabilities that you can use on AWS to improve the price, performance, and experience to run your Windows workloads. Quickly walking you through the agenda for today's episode, we'll start by providing you a quick overview of how we've seen compute layer evolve over time and key capabilities and features that we offer as a part of supporting Windows Server on Amazon EC2. Then, we'll walk you through a cool capability that we launched last December to improve launch times of your Windows instances along with a demo. Then, we'll walk you through containers all the way from top use cases that we've seen customers leverage containers for, the container options available on AWS, benefits and caveats of using these options, and then we'll talk you through a demo of deploying Windows containers on AWS and our top tips to run Windows on AWS. And finally, we'll close on by sharing a quick guidance on how to choose right compute for your Windows workloads. If you have any questions along the presentation, please feel free to type them in the chat window at any time, and our team will be happy to answer them. Before we jump on to discuss various compute platforms that you can use to effectively run your Windows Server workloads, here's a quick overview of what we offer in terms of capabilities and experiences across your legacy Windows workload lifecycle, such as migration, be it a lift and shift to EC2 or re-platform and refactoring along the way, to managing and ongoing operations and performances, utilities, storage, etc. We strive to provide the best flexibility, performance, and experience to our customers. Given today's topic is all about compute platforms for AWS, here's a quick rundown of how we've seen an evolution in this space. Going from, of course, traditional data center deployment with complete ownership and management of underlying hardware, to identifying ways to move to a virtualized environment and improving hardware utilization, to now, of course, be seeing a transition and a shift towards containers to package and run applications across diverse environments on premises and in cloud. Containers, of course, provide a lightweight, isolated environment that makes your applications easier to develop, deploy, and manage. Containers start and stop quickly, making them ideal for apps that need to rapidly adapt to changing demand. And the lightweight nature of containers also make them a useful tool to increasing the density and utilization of your infrastructure. Let's talk about virtual machines, or EC2 in this case. First and foremost, to support Windows Server on EC2, we offer prepackaged Amazon Machine Images, or AMIs, that contain the information required to launch an instance. You can choose an AMI based on Windows Server versions, AWS region you wish to operate in, 32-bit and 64-bit architecture, additional software like SQL Server, and so forth. In addition to these prepackaged AMIs, we also give you the option to create your own customizations to these base Windows Server images using EC2 Image Builder that you learned about in one of the previous episodes. Or you can also create an AMI from software running on your own Windows computer. Next, with the AMIs that we offer, we also provide latest Windows drivers such as NVMe, PV, and ENA. These versions and Windows patches are updated every month, And you can also use Systems Manager automation runbooks to apply driver updates across your existing instances. You can also choose across various licensing options. You can use license included if you don't want to deal with complex Microsoft licensing terms and just buy licenses from AWS. Or you can bring your own licenses if you want to leverage any of your existing licenses and leverage dedicated hosts to run your Windows Server workloads. You can also leverage EC2 savings plan to get the lowest prices for your workloads. And finally, you also get options for instant storage, which is EBS, file storage, as well as the one that you get with the instance directly. And finally, EC2 Windows fast launches, as the name suggests, improves the launch times for your Windows Server instances. So let's talk a little bit about how you can configure your Windows Server instances on EC2 for faster launching. So as you know, Windows Server OS launch times can be a source of costly delays while provisioning resources for mission-critical workloads and recovery processes. While we've been offering fast launches for AWS offered armies and continue to improve launch times for instances created using these armies, launches done using customized images often don't have the same launch times. And to improve this, about 9 months ago, AWS launched the ability to create Windows Server instances up to 65% faster on EC2 using custom images. As you can see, in the past, while these images would take up to 242 seconds to launch, we've brought these numbers down to up to 85 seconds, and in some cases, even as low as 40 seconds. The way to get started is that you can flag a custom Windows Server army for faster launching, either in the Amazon EC2 console or via API or CLI. The capability reduces provisioning time through faster launching and allows you to quickly access compute resources to meet dynamic demands of your workloads. You can also process scaling requests much faster in DR scenarios using this capability. You can also use this to address spiky demand curves of your workloads faster in meeting business requirements. And finally, failover and recovery applications can also access instances faster, which saves you critical seconds and avoids data loss. Quickly giving you an overview of the cost, there is no additional charge for using this capability. You do get charged for underlying AWS resource usage, which is S3 in this case. And to give you an example, if you were to use 20 instances and use fast launch on these instances from an army per day, you would expect a charge of up to 2 cents per instance launched. So now we'll have Marcio walk us through a demo of how to enable Windows Server armies for faster launches on EC2 and share how the capability works before we move on to talking about Windows Container Platforms. As a reminder, if you do have questions, please feel free to add them to the chat box so our team can answer them as we go through today's workshop. Marcio, over to you.
All right, so thank you, Purvi. So before we begin, for those that doesn't know what is an AMI, it's an Amazon Machine Image. It's a supported and maintained image provided by AWS that provides the information required to launch an instance. But there are times that you need to customize those provided AMIs from AWS. You need to install the necessary softwares or patching or hardening those AMIs. And those are, once you do that, the name, it becomes a custom AMI, right? So in this demonstration, as Purvi just said, I'm gonna show you how to enable fast launch for custom AMIs. So the first thing you need to do is through the EC2 Web Console. And through the EC2 Web Console, you click on AMIs under images. And once you search for your custom AMIs, as you can see here in my example, I have two AMIs. One I call as a fast launch enable, the second one fast launch disabled. So let's say, as an example, that I want to enable fast launch in this specific AMI over here. So I just click over the AMI, and then I go to action. Within action, I have the option called Manage Image Optimization. Once I click on Image Optimization Settings, I have this option here called Enable Windows Faster Launch. And once I click on it, I receive two new options. The first one is to set the number of pre-provisioning snapshots that can be ready for launch within the time frame specified. So let's say your workload has dynamic spikes, right? So you are using auto scaling to handle the traffic, and through this 1 hour, you scale out and in, and through this 1 hour, usually you launch 5 instances per hour. So you can select between the number of EBS snapshot that is going to be ready to go once your environment scale out. So let's say from 5 to 15, but you can also customize. Once you select the number of EBS pre-provisioning you need in order to accommodate the traffic that comes into your application, you can click Save Changes. But let's say you also use EC2 auto scaling, and EC2 auto scaling, it uses launch template. So you can also enable the custom AMI with Windows Fast Launching directly in the launch template. So in this an example here, I'm gonna select just 5 launches per hour, and I'm gonna click Save. So coming back to the EC2 instance dashboard, let me show you here what actually happens behind the scenes. Let me refresh my number of EC2 instance here. And as you can see, I already have 5 EC2 instance that is being launched. What that means? So let me explain. When you create a Windows AMI, Windows Server by default, there is a functionality called sysprep. Sysprep is a Windows Server or a Windows desktop mechanism that generalize a Windows Server image. What that means is imagining that you want to harden or install specific softwares in a Windows Server image, and you want to redistribute this image to launch any number of servers. So you want to reuse that image. So the process I just told you called sysprep generalize the image by removing something called security identifier, SID. Each Windows server or Windows desktop has a SID number, is a random number that identifies that server. So when you create the AMI, the sysprep happens removing this SID number. So you can reuse this image from any number of EC2 instances you want to launch. However, at the time you launch a new EC2 Windows instance from that custom AMI you just created, the sysprep process kicks in. And instead of removing this SID, as it did in the past by creating the custom AMI, now the sysprep actually creates a random ID for that EC2 instance. This process, as I said, is built in on a Windows Server and desktop, in a Windows desktop, and it takes time. There is nothing you can do to control that process. So at the time you enable fast launch, and as you can see here, we pre-provisioning EC2 instance that match the number of launches you specify when you were enabling fast launch. So the process of launching EC2 instance, the sysprep kicks in, and once it finishes, the fast launch feature takes a snapshot of that state once the sysprep ends, and store it as an EBS snapshot on an S3 bucket in your account. So the next time you launch a new EC2 instance based in this custom AMI, instead of going through all the way down to the sysprep process, the EC2 control plane is going to use this snapshot, which was created by fast launch, and attach it to the EC2 infrastructure, EC2 instance, and you are ready to go. So let me show you some examples here. So let me filter by the instance I just created. So I have two instances. One I launched from a custom AMI without fast launch enable. And the second one, I launched a custom AMI with fast launch enable. So let's see how long it takes for a EC2 Windows instance without fast launch based on a custom AMI to achieve the status of running. So here is an example. When I launch this EC2 instance, I did a EC2 API call at 7 p.m. 7 p.m. in 30 minutes, right? However, this is when I launch, this is the launch time. But the time it takes to the Windows server to be ready to go, it needs to go through this sysprep process I just said. So if we look at the syslog of this EC2 instance, you see that the time it took for the instance to be ready is 37. So this is a different time zone from the hypervisor, but just focus here on the minute itself. So as you saw on my EC2 console, my EC2 launch instance API call happened at 30 minutes. But then my Windows instance only became ready after 7 minutes. And this is pretty much because the sysprep that I just told you took around 6 minutes to be completed. And as I said, this is a built-in functionality on Windows that you can control. So from the time I created my EC2 instance to the time the sysprep finished, it took 6 minutes just to complete this process. And then the EC2 control plane took 1 more minute to launch my instance. Now, if you want to accelerate this process, also enabled by fast launch, what you could do, this is an example. I launch a EC2 instance, and let's take a look here on in the minutes itself, right? So I launched this instance pretty much at the 36, right? And let's see how long it took for this instance to become ready to go. So let's see 36, right? 30, 35, 59. So if you can click here and go to the syslog, what we can see is that this instance become ready in just 2 minutes, right? So from the 36, it took around 2 minutes for this Windows instance to be ready. So when comparing with another example that it took 7 minutes to be ready to go, where 6 minutes was used by the sysprep process, with a fast launch, we reduced that amount to only 2 minutes. So this is a great example where you can accelerate the EC2 Windows startup time, especially when you use applications that needs to handle dynamic traffic to scale out any. But not only that, you can also monitor the fast launch through Amazon CloudWatch. So in this example here, I'm using a metric from the EC2 images. And as you can see, I have the count number of 5. So this is the number of pre-provisioned EBS I selected when I enable fast launch. And when I launched this EC2 instance for the demo, as you can see, it used one EBS snapshot from this bucket. So it went down to 4, but once this instance become ready, the fast launch control plan kicks in and pre-provisioning another DBS for me to always keep the number of pre-provisioned DBS full. So this is what happened. Here is a refill, right? So I launched an EC2 instance. It took one pre-provisioned EBS, and then the AMI fast, the EC2 fast launch just refill the bucket to achieve the number I specified all over again. Cool. So now let's shift gears and talk about Windows containers. So let's talk now about running Windows workloads on AWS container platforms. So we have seen some trends with our customers that customers are willing to use Windows containers, right? So customers figured out like it's easy to containerize a Windows application and leverage all the container platform and container ecosystem to run those kind of legacy applications per se. And we have seen some use cases across the board. We have seen customers running .NET and ASP.NET applications as a Windows container, but also we have seen customers running COTS application. So COTS applications, those who are developed by third-party companies, on supported as a Windows container, you are ready to go and use. But also we have seen the online game industry leveraging Windows container, from hosting multiplayer server games for matchmaking applications for online games. But not only that, we have seen customers also adopting Windows containers for cost optimization and management operation. What that means, as Purvi just said, when you adopt containers, independent of being Windows or Linux, you are able to achieve more application density per server. So thereby reducing the number of EC2 instance, Windows or Linux, you need to run the exact same number of applications. So as a customer, if you decide to run Windows containers on AWS, AWS has the broadest and most complete set of compute to run Windows containers. You, as a customer, you can decide between running your Windows containers on AWS Managed Orchestrator or Self-Managed Orchestrator. From the left side, the AWS Managed Orchestrator, you can use Amazon Elastic Container Service, or ECS, which is a container orchestrator built by AWS with deeply integration with other AWS services, such as Managed IG, or Amazon FSx for Windows File Server, or AWS IAM, and etc. But let's say you want to leverage the Amazon Elastic Container Service as an orchestrator, but you are required to run this Windows container on-prem due to compliance reasons. So you can use Amazon ECS or Amazon Elastic Container Service anywhere. But you also have the option to run Windows containers on Amazon Elastic Kubernetes Service, EKS. If you're already running applications on top of Kubernetes, or if you are planning to adopt Kubernetes as your default orchestrator, Amazon Elastic Kubernetes Service supports Windows containers as well. In all those three options I just explained about, all those options require you to manage the EC2 Windows operational system. But if you just want to run Windows containers and you don't want to manage the underlying operational system of EC2 Windows, you can choose AWS Fargate, which is a launch type within Amazon ECS. So with AWS Fargate, you just specify your Windows container image, you select the amount of CPU and memory you want, and you are ready to go. Just launching your container, and there is no Amazon EC2 Windows instance to be managed. But on the other hand, there are customers that requires to manage not only the whole Amazon EC2 Windows operational system, but also the container orchestrator. So for this specific use case, customers can run their container orchestrator like OpenShift, Rancher, Nomad, Kubernetes, and etc. on top of Amazon EC2 Windows or on VMware Cloud on AWS or AWS Outposts. So you have different options that fits on your specific use case. Now, let's talk about container management lifecycle. So I was talking about how to run Windows containers on AWS, but you can also use the same compute platform to build your Windows application. So let's say you are developing a .NET full framework application or ASP.NET full framing application. You can build this application using Windows containers on Fargate, EKS, or ECS. And those same applications, once built and containerized, can be also deployed on top of this exactly same platform, Fargate, Kubernetes on ECS. So the container lifecycle, once you build, you deploy, and then you need to monitor, right? Observability, and you can leverage Amazon CloudWatch metrics and Amazon CloudWatch container insights for those monitoring, which I'm gonna show you in a demonstration in a bit. Now, let's do a high-level overview of Amazon ECS for Windows containers. So if you decide to run Windows containers on an Amazon ECS platform, the Amazon EC2 Windows instance you deploy, we call as a container instance. And with ECS, we have something called a task definition. A task definition, think as a blueprint for the configurations you want within your container. So let's say you want that container use X amount of CPU and memory, but also you want that container to integrate with Amazon CloudWatch logs or have persistent storage. All those configurations are specified in a task definition. And then when you are ready to run these Windows containers on top of Amazon ECS, we run a task. So a task is a logical group of containers. And within the container instance, we have something called ECS agent. And the ECS agent is responsible to exchange communication with Amazon ECS control plane. So by starting new tasks, terminating tasks, or creating services. So this first example I just show you, which you launch Windows containers in a form of task, we call it as a standalone task. Usually, a standalone task is used for short running containers, like a pooling mechanism on your application. But let's say that, for instance, you need to host an ASP.NET application as a Windows container. So this is going to be a long-running container. And for this specific functionality, Amazon ECS provides something called service. A service on Amazon ECS, you specify the number of tasks or Windows containers that you need to be up and running. And the Amazon ECS service is going to be responsible to keep that number of tasks up and running for the period of time. But not only that, with the service, you can specify application load balancer or a network load balancer to route your traffic within the task or the Windows container. Great. This is a high-level review of Amazon ECS for Windows container. Now, let's talk about Amazon EKS for Windows containers. For instance, you want to use Kubernetes to run your Windows container. So when you create an Amazon EKS cluster, it creates in our control plane managed by AWS the API servers, and the etcd database to support a Kubernetes cluster. But also for Windows containers, we deploy the VPC controller, which is responsible for your Windows containers in a form of a pod to have an IP from your VPC DHCP pool. So once you create your Amazon EKS cluster, the cluster is composed by the control plane, as I said, and the data plane. And you are responsible for the data plane. The data plane means the EC2 instance that you are going to manage and launch in order to host your Windows container. Amazon EKS, for Kubernetes, actually, we call it a worker nodes, but on Amazon EKS, we call it a node groups. So you can have multiple node groups with different Windows Server versions, like Windows Server 2019 or 2019 SAC versions, if you need it. And now, let's talk about AWS Fargate for the Windows container. So I just explained to you Amazon ECS and EKS. So in this picture, this is actually what happens when you are running Windows containers with both options, ECS, EC2 deployment, and Amazon EKS. So you build your container image, you define and deploy the EC2 instance size you want to run those containers, and you provision and manage the compute and memory resources for those containers, right? There are cases where specific applications require kernel isolation, which is not offered by default in a container ecosystem. So you deploy very specific Amazon EC2 instance just to host those specific Windows containers. And then you run and manage both the application and the infrastructure part. And you pay for the EC2 instance. So that's fine. But let's say you want to run Windows containers, but you don't want to manage the EC2 Windows platform. So what you can do with Fargate, you build your container as the same as you would do with running your container as a EC2. But then with Fargate, you just define the memory and compute resources required to run this container, and you are ready to go. You pay for request compute resource when you use it, and that is it. But to run containers or Windows containers, you need to build this container image. So let me go for an example on how can you build Windows container image on AWS. For instance, you are using the AWS development tools, and you just set up a CI/CD pipeline, and you are using your code, and we are using AWS code pipeline to work as a pipeline for your CI/CD. And then you decide to use AWS code commit to be your Git repository. And there you have your Docker file, right? We specify your base image, and then all the necessary commands that needs to be in place for your Windows container image and the application work. And then through this pipeline, you can kick in the AWS code commit. So once you commit the code on your Git repository, AWS code build initiate the action. And you can instrument AWS code commit to build your Windows container image using Amazon ECS, Amazon EKS, and AWS Fargate. Once your container image is built, you can also instrument AWS code build to store this Windows container image on Amazon CR. And once you do that, you're ready to go and use all the containers platform like ECS, EKS, and Fargate and launch this Windows container application. So in this demonstration, I'm gonna deploy our Windows containers on AWS. I'm gonna first show you how to deploy a Windows container using ECS Fargate, and then I'm gonna show how to launch exactly the same image on an Amazon ECS based on EC2 windows. And finally, I'm gonna use Amazon EKS to launch exactly the same Windows container. For the Amazon ECS console, I already have some cluster deployed. So my next step here is to create a task definition, which I said is a kind of a blueprint which you define CPU, memory, persistent storage if needed to run your Windows container. So let's take a look at how to create those. So you click on task definition under Amazon ECS console, and you can click in create new task definition. In the console, you need to specify the launch type. And as I said, using Amazon ECS, you have two options, Fargate or EC2. Let's start with Fargate first. You select Fargate and click Next Step. So let's give it a name. As an example, hello world 01. Then it's optional, but you can specify an IAM role so the task can assume this IAM role and do some API requests to AWS services. The next step is to select the operating system family. You can choose between Linux, Windows Server 2019 Core, or Windows Server 2019 Full. We do recommend for you to use Windows Server 2019 Core for Windows containers. The next step which you can select is the task execution role. Right? The task execution role is required by tasks to pull the container image from your Amazon ECR if the image repository is using Amazon ECR. And then you can specify the memory and CPU for the task size. This is an example. My Fargate task is going to be a 4 GB and 2 vCPUs. The next step now is to actually specify the container definition. So as an example, the name of my container, (01). So hello world, and just use dashes here. And then you can specify the container repository. Your image, in my case, I'm using the MCR from Microsoft as an image repository. So I just brought it from the Docker Hub as an example. Next, you need to specify the memory limits, soft or hard limit. Right, so I'm going to specify a soft limit of 512 megabytes. And then port mapping. So I'm going to expose my Windows container on port 80. And I'm going to just click next as a simple example. And then click create. So once you click view task definition here, I just create this task, right? The hello world 01. I can also create new revisions if needed, if I need to change, because remember, a task definition is immutable. You can change. You can create new revisions if you need to edit any configuration, right? But if you're ready to go, what you could do is just click run task. You can select the launch type. So I created the Fargate, my task definition based on Fargate. And then I can select the operation system. So I need to select exactly the same operation system family I choose when created the task definition on the launch time. So in that case, the Windows Server 2019 Core. And then let me just specify a different cluster here. And Windows Server 2019 Core. And then you need to specify a VPC, right? So I am just specifying a VPC I already have, and the subnets, I'm gonna deploy it on my private subnet. And also you need to specify the security group, right? So in this example here, I want to create a new one for all traffic from HTTP on port A and click Save. And I don't want this Fargate task to have a public IP. So in my example, this Fargate task is going to be used only by the private network. And then you can click Run Task. Great. So just for a matter of time, I already have this Fargate task running over here, right? So I just launched its provisioning, it's pulling the container image from the repository, and then it's going to launch the Fargate instance. But now I already have this one here. So let's take a look. If I want to access this one here from the internet, this is an example that I already have one running. It's a public face Fargate task. And as you can see, I'm running the IAS Windows container. This is the IAS default web page, right? So the beauty of this is that there is no EC2 Windows to be managed. It's a serverless Windows container. Now, let's go through the same, but launch this Fargate task based on our ECS EC2 deployment. So from the same console, what I need to do, I just need to go through the exactly same steps I just showed you guys on how to create this task definition. And then I can select this task definition as a hello world here, click in action, and run task. The only difference here is that the task I created to run as a EC2 deployment and not Fargate. So I select EC2 as a deployment. And let me just change my cluster here one more time. And then you can specify the number of tests that needs to be in place once I launch this task. So, and then I click Run Task. And for a matter of testing, as I said, I already have ECS EC2 task up and running here. So one is the Fargate I just showed you, and now this one is based on EC2 deployment. As you can see here, the launch type, right? So you have Fargate and EC2. So let's take a look. And I'm gonna copy and paste the IP of this ECS EC2 deployment task. As you can see, my external link is only a private IP because I don't want to expose this container to the world. So what I can do here is just going through my VPC internally. And again, we have our Windows server, our Windows container actually running this IAS default web page. So as you can see, it's very straightforward to run your Windows containers on ECS Fargate or ECS EC2. Now, let me show you how you can do the same, but using Amazon EKS. So on Amazon EKS or Kubernetes, we use manifests. And manifests is how you specify the Kubernetes services and deployments to run your Windows container. So in this example here, as you can see, the image remains the same, right? I'm gonna pull the image from the Docker Hub, and I'm just gonna change here for our image to give us a hello from Amazon EKS. And I'm gonna save this manifest. The next step is to actually run this Windows container in a form of a pod on Kubernetes. So what I can do is to run this container. So let's take a look and see the status. And as you can see here, I have my container in a creating mode and is ready to go. So very fast, right? So now I want to access this container. So what I want to do here is just access the endpoint I just created, my deployment, and check if it's available. So again, as you can see now, this is hello from Amazon EKS. So exactly the same image we were able to launch on Amazon ECS with Fargate deployment type, with Amazon ECS and EC2 deployment type, and then on Amazon EKS. Very straightforward. Cool. So let's move on. Now, let's talk about our top tips for best practice. The first one is to avoid image pooling during runtime. What that means is you can use a pre-cache image strategy directly within your AMI. So you can use Amazon Image Builder as an example to build your custom AMI and pull all the necessary Windows container image layers that needs to be in place to run your Windows container. So at the time your Windows container host kicks in and is ready to launch new containers, you will avoid pulling all those big images from a Windows image, and then you can achieve a better performance through the container from the Windows container launch time. As I don't know if you noticed, but in my demonstration, when I launch my Windows container on my Amazon EKS cluster, the Windows container becomes ready in a matter of seconds. So this is because I used the pre-cache strategy on the AMI when I was using that container host. The second one is treat your container instance as a ephemeral host. What that means is that usually as a Windows administrator, you do patching, hardening, you reboot your instance, you need to run agents for inventory and so on, because your application is installed directly on the operational system. When you choose to use Windows container, actually, the application itself lives in the container. So it's out of the container instance or the Amazon EC2 instance. So in that Amazon EC2 instance, there is nothing there. Your application is not there. The only thing you have is the container runtime. So with that, you can treat your container instance as ephemeral. What that means is if you need to update your container instance, you just terminate this container instance, bring a new one with a new AMI that you just prepared with all the necessary updates you need. If something goes wrong with that container instance, instead of troubleshooting, you just terminate and bring a new one. So this is the new way you need to manage your Amazon EC2 windows when working as a container instance. The third is rebuild your Windows container image frequently. Remember that Microsoft releases security patches every month. So in order to have those security patches as part of your Windows container image, we do recommend you to constantly rebuild your Windows container image through your CI/CD pipeline. And fourth, use Instance Store to reduce cost and improve performance. Containers itself are ephemeral, right? They do not persist any data. So instead of using Amazon EBS to work as a storage for your temporary Windows container, one of the options you can do is to select an Amazon EC2 instance that offers Instance Store and use your container orchestrator like ECS or EKS to point all the pooling images to this Instance Store storage. So with that, you are not going to be paying Amazon EBS for those temporary container instances, but also you're going to improve performance as Instance Store offers better performance over Amazon EBS. Let's talk about compute decision process. As an example, you have an application you want to migrate from on-prem to the cloud. So you should ask yourself, is this a lift and shift? What that means, I want to migrate my virtual machine on-prem to AWS? If yes, do you want to have control over the virtual machine, the operational system, the storage, patching, and antivirus? If yes, Amazon EC2 instance is your choice. However, if you don't want to control patching, VMs, or monitoring on those virtual machines or Amazon EC2 instance, you can choose AWS Elastic Beanstalk. And the AWS Elastic Beanstalk is a managing services offered by AWS that deploys an Amazon EC2 Windows instance, manage those instances, apply patch, and monitoring for you. So you just need to build your application and run as a Beanstalk environment. However, we also need to ask ourselves, is this application architecture service-oriented? If yes, is this application containerizable or not? If yes, you also need to ask, is a legacy .NET framework? What that means is it uses the .NET full framework instead of .NET Core. If yes, and you want to use as a Windows container, then containerizing this application in a form of a Windows container is an option. But if it does not use .NET framework, full framework, you can ask yourself, this is a long-running service like a web application? If not, you can run this application in AWS Lambda. But if it is a long-running, you can choose to run this application in a Linux container. Once you decide if you are going to keep this application in a .NET full framework and run as a Windows container, or in a Linux container using .NET Core, the next question is, do you have expertise in-house to manage and control a Kubernetes environment? If so, Amazon EKS is your option as a Kubernetes management offering. But you can also ask, okay, do I need control over the container host? If not, you can choose AWS Fargate and run your Linux and Windows containers. But if you need to have control over the container hosts, like managing your Windows server, etc., then you can choose Amazon ECS. As additional resources, we have our official documentation around Amazon ECS, EKS, and Fargate. We also have blog posts we usually publish with a step-by-step process on how you can create Amazon ECS, EKS, and Fargate clusters, but not only that, how you can tune and set up specific configurations in those clusters. In addition to that, you can check the aws.amazon.com/windows/FAQ for more information. Thank you.